Today we will review the paper, Probing the 3D Awareness of Visual Foundation Models, from University of Michigan and Google Research. The key question the paper is trying to answer is that visual foundation models are great with 2D vision tasks, but can they also encode and understand the 3D structure hidden behind these 2D projections? They picked some of the most popular models and test their ability to represent depth, orientation, and view invariant spatial relationships. Now let's dive in. First, we need to define what is 3D awareness. In this work, it is defined by two core capabilities. The first one is single-view 3D surface reconstruction. This is the capacity to infer depth, surface orientation, and overall geometry from a single image. The second one is multi-view consistency. This is the ability to maintain consistent representations of objects or scenes, regardless of viewpoint changes, reflecting a grasp of underlying 3D geometry. These two capabilities mirror human-like 3D perception, from recognizing how far objects are in one snapshot to identifying them regardless of spatial viewpoint shifts. The authors probe different models by adding a DPT decoder to the original models and train for different tasks. DPT represents Dense Prediction Transformer from the paper named Vision Transformers for dense prediction. It is a multi-scale dense probe to map the features from multiple layers. The authors also mentioned that they did not choose a linear probing on a specific layer, because it is unclear why we should require the encoding of 3D properties to be linear. Furthermore, the model may represent such properties at different or multiple locations within the network. Notice that we are doing probing, not fine-tuning. The model weights are frozen, the probe weights are task-specifically trained. To ensure the observed 3D understanding is the inherent capacity of the original models. The study examines a variety of VFMs, categorized by their training objectives, to see if different architectures and training objectives have impact on 3D awareness. Now, for the first core capability that defines 3D awareness, let's look at single-view 3D reconstruction. This capability is probed in two tasks: the task of monocular depth estimation, which predicts per pixel distances, and the task of surface normal estimation, which predicts per pixel surface orientation. Looking at the results, we have found that models vary widely. Some only capture coarse geometric cues, others yield fine-grained depth and normals. Among the models, discriminative self-supervised models, Dino V2 and generative models, Stable Diffusion XL, capturing fine geometric details, suggesting self-supervision and generative training can foster robust geometric encoding. However, vision language models, ECLIP, underperform, relying more on general scene priors than precise depth understanding, hinting that semantic focus may come at the expense of spatial structure. This diversity in performance highlights that not all training strategies equally promote geometric understanding. The best performers were not explicitly trained for 3D tasks, yet still encode rich surface cues. The second core capability for 3D awareness is the multi-view consistency. Here, the task is geometric correspondence estimation, identifying the same 3D points across different views of the same scene or object. From the result, we can see that the models perform well with minimal viewpoint shifts, but struggle as viewpoint differences increase, indicating limited 3D consistency. Some models show steep decline. Stable Diffusion and SAM, which are strong in single-view tasks, suffer notable drops under large viewpoint differences. And we can observe a gap between semantic and geometric understanding. Models align semantic parts well, but fail at true geometric consistency when angles diverge, suggesting they may rely more on semantic cues than genuine 3D understanding. The limited success in view invariant correspondence suggests that these models often rely on view-dependent or semantic cues rather than forming a stable 3D mental model. These experiments revealed some key insights. Firstly, single image 3D awareness is surprisingly present in many models. Many large scale VFMMs, despite being trained for completely different tasks like classification or self supervised learning, exhibit a non trivial capacity to represent basic 3D attributes. However, the next insight is that multi-view consistency is still lacking. While models can sometimes match corresponding points across small viewpoint changes, performance deteriorates significantly for larger viewpoint differences. None of the surveyed models maintain robust 3D consistency across widely varying perspectives. And lastly, models known to do well in semantic correspondence do not necessarily have strong geometric consistency. They may align similar semantic features, but fail to account for changes in viewpoint. This confirms that strong semantic capabilities are not the same as understanding 3D geometry. At the end, some of the future directions are discussed as well. For example, develop more rigorous and geometry-focused benchmarks. Investigate how specific training objectives influence the emergence of 3D features, and explore methods to foster view-invariant representations. In my opinion, this work is a stepping stone, guiding us towards strategies that refine VFMMs into models that truly understand the 3D world.